I would be talking about chiplets for the future of AI. So let me give you a quick outline. I'll talk about the explosive growth of AI, which includes the growth in the model sizes and the compute demands, the requirements that we have for AI systems, and then how does heterogeneous integration play a role and will continue to play a role to meet these demands, and what do we see as the path forward? So I think this is a little bit of an older slide, but I think it motivates well that everywhere AI has just become pervasive, and its growth is truly exploding. It's going into every aspect of our lives, from image processing and object detection, natural language processing, facial recognition, medical application, sentiment analysis, and the list can go on and on. And what this has led to is this enormous growth in unstructured data. And you can see the bottom blue part here is what we traditionally call structured data. That's what computers were really good at, and human brains were good at this other part. But now we have learned how to make computers understand unstructured data more like the human brain. And as a result of all of these kinds of applications, we're facing an unprecedented growth in the amount of data that needs to be processed. So the AI capabilities are broadening and generalizing. So this chart actually is a few years old, but I thought it was very illustrative because when we first presented this chart, we were back somewhere between the light blue and the dark blue, the narrow AI and the broad AI parts of this. And at that point, AI was becoming very good at single tasks, single domains, maybe superhuman. There was a great point at which AI programs were beginning to exceed human accuracy and speed for certain tasks. They could recognize, say, breeds of dogs better than a human could, and that was considered to be a huge triumph. And then that was expanding to multitask and multi-domain, multimodal, and using more than one AI chip or node or system, and beginning to get a little bit more on the way of explainable. So it wasn't just a mysterious black box. But now we're at a very exciting point in our history where we're talking about the part on the right chart of this graph, which is on the general AI, cross domains, learning, reasoning, broad autonomy. And I think everyone has seen the astounding implications of this, as well as the capabilities. So we're in an extremely exciting time. But this movement from left to right has also meant that the compute demands have just extraordinarily grown, and we have to find ways to meet these. Just to give you an illustration, this is how the model sizes have been growing. So the AI algorithms depend on a model, and back in the mid-2010s, we were on the left side of this chart. You can see some of the sizes of these models, ResNet 50 and DenseNet. Fairly small models. And then we moved to this red curve. Now, this red curve talks about models which we can now generally call foundation models. These are very large AI models that can be adapted to a wide range of downstream tasks. And the trend today is that we train one of these big models with some sort of general training, and then we can do a specialized training for a particular task, much the way a human learns a general set of education and principles and then becomes specialized to become an expert in one area. The thing is that the size of these models has been growing astronomically. You can see that the transformer size here is growing at a rate of 410 every 2 years. And we have to keep up with this in terms of the memory demands, but the green curve illustrates that the AI hardware memory is maybe scaling at a rate more like twice or double every 2 years. So that leaves a large gap, and we have to think about how can we start to meet these demands. Now, in addition to the memory demands and the model sizes, we have to compute on these, and so the AI compute demands are also growing exponentially. This chart shows the training compute that is required in order to train one of these models, and you can see that the red curve here at 750x every 2 years is vastly outpacing what we might expect, or as Moitri said, from Moore's law. So we really have to begin to look at what else can we do in order to meet these extraordinary demands. So let me go on to a little bit of a deep dive on the AI requirements, including the compute requirements, the memory bandwidth and capacity requirements, and the connectivity requirements. So first, just as a little bit of an introductory or a tutorial, let me talk about deep learning and training requirements versus inference requirements. So the way training is normally done is there's a large body of data and a neural network, which you see here in the middle, and that the data is passed through the neural network, and then the neural network makes a prediction or a classification, and then that is compared to a ground truth or a label to see whether it's correct or wrong. And if it's correct, that's great. And if it's not correct, then we have to go back and do a step called backpropagation, in which we adjust the weights in the neural network to make it a higher chance that we will make the correct prediction next time. That's what training is. But once we train the model, then we don't have to go through this, this comparison step and backpropagation again. What we can do is just propagate whatever data we have at the left to the right and make a prediction. So that's computationally an easier step. These use cases are, of course, quite different, but the underlying math between them is really the same. Inference is then just really a subset of training. And you can see that these can differ in some significant ways. In terms of the compute phases, the training involves this forward pass, a backward pass, and an update phase, whereas the inference involves just the forward. For training, we need a lot of input data. So that is what we call a batch size, and that can be very large. For inference, it really depends. In many cases, like an ADAS application, if you're in your car, then what you're looking for is low latency for the AI algorithm to just quickly make a prediction. And there's really only kind of one or a small number of inputs. On the other hand, you could also think of a batch processing. For example, a large bank may have want to do, or an insurance company may have to do a lot of processing on a given model, and so the batch size in that case could be large. The memory footprint training is much more memory intensive. This is because actually in this backpropagation phase that you see, you have to retain a lot of the data structures that you may have generated during the forward phase. There are activations that have to be kept, and there are other optimization parameters for the training. So the memory footprint tends to be very large. For inference, it can be much smaller. Typically, training requires a very distributed system. You hear about these large racks of GPUs that are used to train AI models, whereas inference can often be done on a single device. One thing that happens is you can often prune a model after training it, or you can do what's known as quantization-aware training. So you purposefully work towards making the model smaller or more containable so that it can eventually fit into the memory of a single device. And in terms of performance, typically for training, because there's a lot of input data, the throughput is very key. Whereas for inference, throughput is also key, but what could really matter in this case is the latency. In other words, the amount of time it simply takes to get a prediction out. And that could be true for, say, an ADAS application for automotive. It could be true for a fraud application where we quickly want to determine whether a transaction is legitimate or not. So latency can play a very key role for inference. So I talked a little bit about the compute requirements, and they can be similar across different types of neural networks. The fully connected DNN that you see on the left, what are known as convolutional networks, where you're just looking at portions of a picture at a time, or the types of LSTMs or recurrent neural networks that you see on the right-hand side. This was an analysis that was done early from our group, looking at the various kernels and what are the operations that are required. And by and large, these tend to get dominated by GEMM or matrix multiplication operations. So that's certainly one thing that an AI accelerator would focus on in order to accelerate these kinds of workloads. And generally speaking, there's a small set of building block operations that are used by all networks, and they are particularly amenable to hardware acceleration. So in this case, what you can see is more than 70% of the operations in matrix multiplication and the convolution operations. So in terms of these compute requirements, two of the things that have really helped to accelerate these operations in accelerators are, number one, the fact that it's a data flow architecture can be of great help. So what do we mean by this? You see here an array of processing elements, or PEs, which are really tuned towards the operations that you saw before. They're able to quickly pass data from one to the other, and they can also keep data in these local scratch pads that are shown here in light blue. And that's a huge benefit. Now, how do we distinguish a scratch pad, say, from a cache, which is often used in computer terminology? A cache is a lot of guesswork. It's trying to guess what is the next best piece of data that I could pull in based on spatial or temporal characteristics. Whereas for these neural networks, the good news is that it's all really predictable. So we know exactly what piece of data we might need at a certain time. The real work comes in prioritizing what data structure should be put in the scratch pad as opposed to being, say, left off chip. But these scratch pads have proved to be enormously beneficial in terms of accelerating these algorithms, because they allow us to, say, keep the weights of the local weights of one of these neural networks in a scratch pad and keep it close to where the processing elements needed based on, say, the amount of time or the number of times that you have to reuse that particular piece of data. The other huge benefit in these accelerators has been in using reduced precision. So actually, IBM started this trend many years ago with some very seminal publications around the 2015 time. And you can see that the top shows you the precision that's required for training to achieve equal accuracy or for inference in the bottom curve. This equal accuracy is very important because you can start to reduce these precisions, but if they don't give you accurate results, then their benefits are rather limited. So you can see that there's this trend to getting ISO accuracy with less precision as you move down, and that's a huge benefit both for speed, power, and chip area. Now, in terms of the memory requirements, the deep learning has very demanding memory requirements. The bandwidth really has to increase in proportion to the compute gains. So it's really not fruitful to find a super fast accelerator that can do a matrix multiplication incredibly fast if you can't feed it the data that it needs, because it's going to sit idle a lot of the time. And that can lead to low utilization of the compute units. And as mentioned before, these on-chip scratch pads are also very helpful. They can be used to alleviate the bandwidth requirements. The other part, as you saw from the growing model sizes, is the capacity also has to be increased. And processors really need fast access to the weights of these very large models. So from a training point of view, many data structures really need to be kept near processors. The throughput is very important. For inference, as mentioned, the number of data structures you have to keep is a lot less compared to training. One thing that is very exciting is on-chip model storage. So in other words, instead of having to go off-chip to retrieve the weights of the model, if we can either store them in these local scratch pads or possibly in a three-dimensional memory, and I'll talk a little bit about that, that's a very beneficial area. And as mentioned earlier, latency becomes key for an inference application as well. So this was actually a study that we had done a few years ago to really understand this utilization piece, which is we just asked ourselves a question as if we had a genie in a bottle who would be willing to grant us one wish. What would we wish for? And we asked the question of what is the overall system performance improvement if I, say, increased only the compute portion, if I just kept increasing the compute but didn't pay attention to the bandwidth. And then we would sit on this blue curve. On the other hand, we took one of these workloads and we said, well, what would happen if I just increased the memory bandwidth, but I didn't do anything to the compute? You see, you get a better improvement in that case because we are actually limited by the memory bandwidth. And if we can optimize these and increase both the compute and the bandwidth in a very systematic way, we would fall on this green curve. And that gives us the greatest system performance improvement. Now, in terms of capacity, these models are also just exploding in terms of their sizes. And it's very hard for the GPU memories to keep up. They are increasing. What's happening is you're seeing more and more memory packages associated with a particular GPU or a particular accelerator. That's certainly one way to increase the capacity. And you can see that there is this, there is a movement to increase the memory limit, but the model sizes are just growing and growing. The last one I want to mention is the connectivity requirements. So particularly for AI training, which is usually done in a distributed way, the workload can be parallelized amongst many different chips, or they're often called workers. There are many different ways to do this. Maybe the simplest one is what's called data parallelism. In data parallelism, each of these workers takes a subset of the training data and determines the changes to the model. So the model is just replicated many times, and each worker takes some piece of the training data and says, I'll do everything. But once that particular worker gets its results, it has to share them with every other worker in the system. So the weight gradients have to be exchanged. And so this communication really increases with the number of parallel workers. And in a very large multi-chip training system, this communication between workers can actually even begin to dominate the training time. So it's very important to maintain high bandwidth between these individualized workers. The other thing is in terms of the power, it's not just the amount of time. It's very expensive to keep pushing data across these lines. So the closer we can pack things together, and reduce these distances, reduce the energy cost of moving between the workers, the lower the power and the more sustainable the system will be. So in terms of how are we doing for these bandwidths, say, versus the compute, this is a nice summary table. Summary chart. What it shows is that compute power continues to increase. That's the gray curve in terms of hardware flops. The green curve is the DRAM bandwidth, which you can see is far below that 100x every 20 years. Or 1.6x every 2 years. And the interconnect bandwidth is even a little bit worse than that at 1.4x every 2 years compared to 3x for the hardware flops. So this introduces significant performance bottlenecks for these types of AI workloads, both in terms of accelerator to memory bandwidths and peer-to-peer accelerator to accelerator bandwidths. And if these are not addressed, you can get a significant mismatch and low utilization of the system. This is all pointing to the real need for a new paradigm. So this is a chart that I think is often shown. It shows the trend in performance for several different metrics. And what you can see is that the density scaling is really continuing to increase. That's good. But single thread performance is saturated. Frequency is only weekly, maybe weekly decreasing. We're very constrained in terms of power. The way that's, the multi-core paradigm has addressed this is just really increasing the number of cores. That's a very throughput-centric model, which is compensating the stalled single-thread performance with increased parallelism. But if we want to make progress on these emerging, we call them emerging, but now they're becoming more mainstream AI workloads. This is really not sustainable without significant innovation at both the hardware and software level. So we need a new paradigm. And that's where we think that HI, or heterogeneous integration, can play a significant role. In terms of compute, HI gives us the opportunity to have very dense compute modules with optimized architectures for AI. In terms of capacity, it enables us to have higher capacity for these very large models and to have high bandwidths to match gains in this compute throughput. And in terms of connectivity, as I mentioned earlier when we talked about connectivity, having very energy efficient interfaces for the exchange of data. So advanced packaging and heterogeneous integration are really essential to address these bottlenecks and help to improve the overall system performance. So let me now transition into talking a little bit more about heterogeneous integration and advanced packaging. So just to level set a little bit, the goal of heterogeneous integration is to integrate separately these manufactured components or chiplets using these advanced packaging technologies with high density interconnects to achieve a gain in the overall system characteristics and operating characteristics and functionality. So this contrasts with the approaches of the past, which you see on the left, the system on a chip, where you're trying to integrate all of the components monolithically onto a single chip that will lead to a large die size, which is not good for these for the new leading nodes because of yield issues and cost issues. It also locks you into a single technology node for all of the parts of the system on a chip. And many times, parts of this chip may not really scale very well as we go to the more advanced nodes. They're better suited to stay in the older nodes. So by decoupling this and integrating the components as separate chips, we have a lot to benefit. And that's where our focus has been. So this is, there are many reasons why the time is really right for chiplets and HI, as Moitri pointed out. One of them is just optimizing the best node for each of the functions. You can design your compute, memory, and I/O in different nodes for cost and technology optimization. This is an example from AMD. You can see that big central I/O chip is in an older node, 14 nanometer, and the compute chiplets are in a much more recent node, in this case, 7 nanometer. Intel has also really leveraged this in their Ponte Vecchio demonstration. I think there are 46 or maybe even 47 chiplets that you can see that are integrated onto this package. It's, there's a lot that was done here, but it exploits many of the techniques of heterogeneous integration to achieve something that you just could never achieve on a monolithic chip. You can also mix and match. You can see the Intel Agilex FPGA, which has a bridge known as EMIB. Those are the small yellow boxes here, which connect the central FPGA to other components such as transceivers. And then you can see a demonstration. This is more of a research demonstration in the bottom right. NVIDIA had taken one of their GPUs and essentially sliced it into 36 little pieces to create a 36 chiplet inference engine. And these are all connected together using low power, using a low power interface, and then assembled onto a package. But that's some of that is a little bit futuristic. Heterogeneous integration is being used very heavily today in AI. The NVIDIA Hopper, which is a large chip nonetheless, but it has 6 high bandwidth memories. So that's 3D, using 3D for memory stacking. And then typically these are assembled onto a silicon interposer so that you have high density interconnects between the HBMs and that central GPU that can give also a high bandwidth then between the processor and the memory. Then there was a recent announcement from AMD on their MI300. They have made several different variants of this and derivatives of this. There's a GPU version. There are mixed CPU and GPU versions. Typically, these involve combining compute chiplets along with high bandwidth memory. And what you're not actually able to see very well from this picture is that there's 3D stacking of these compute dies on active base dies underneath. So there's genuine 3D as well. So I think these are very exciting demonstrations, but there are many avenues for future research. One thing is the high cost of many of these advanced packaging options. So cost is a driving factor. Greater scalability, because the ability to expand horizontally and put more and more chips or chiplets onto a package is of great benefit, because that will reduce the distances and give us more compute per unit area. Higher bandwidth and capacity to meet the growing needs for AI. Lower power is always helpful, particularly for sustainability. And then more compact form factors. This is especially important for things like on the edge. If you think about telco or automotive applications where space is just limited. So vertical has a lot of appeal in that case. Now looking towards the future, there are really kind of 3 primary approaches in this taxonomy. At the left is the interposer approach. We saw some examples of silicon interposers. That is the mainstream workhorse right now. That's an established technology. An emerging technology for the cost, for one reason is the cost, are these organic technologies. So this is looking at organic laminates and then trying to reduce the design rules so that you can actually achieve things similar to what you would get on a silicon interposer at a lower cost and greater scalability. Another approach, which in this taxonomy is called redistribution wiring, really confines that to the region that's between the die that needs to carry the high density signals rather than the entire die. One approach for that is the silicon bridge. We just saw an example of that in the Intel EMIB. Another approach, which is gaining a lot of popularity these days, is a fan-out wafer level package. These are tied to the back end or to organic redistribution layers in the case of wafer level fan-out. And then a third category, which is now really beginning to take off, is, of course, 3D integration. And one key difference here is that in 3D integration, this does involve active dies with TSVs. So there has to be a modification to the design of, say, the bottom die or dies if there's a multi-stack. And one reason why this is getting a lot of attention is the area of hybrid bonding. Hybrid bonding enables extremely dense interconnects and lower and gives the prospect of very high bandwidth at lower power and potentially even some thermal benefit as well. So, you know, one category here is just finding alternatives to the silicon interposer, because although it is an established technology, it does have a very high cost. And the scalability ultimately is limited. Now, it is possible to stitch together reticle field. That's what leads to larger interposers, but that does become more complex, more expensive. And as you can also see, it does lead to warpage concerns between the silicon and the underlying substrate. So some of the alternatives that are being explored include silicon bridges, where, again, you're only connecting the local areas between the two dies, a wafer-level fan-out package. As you can see, there's also a lower cost alternative whose scalability is really being explored at this point. And then, as mentioned earlier, maybe replacing the silicon interposer with an organic substrate using, say, thin film regions up here, which allow for tighter ground rules and therefore higher bandwidths. The other area is 3D, which we think is very exciting. For 3D, you can get to higher bandwidths. The off-chip memory bandwidth is really limited by the packaging features, whereas here you're directly going vertically, so you can get to much higher densities. And as mentioned earlier, the memory bandwidth has to really keep up with the compute, and keeping data nearby really helps with that. They're also much less expensive in terms of energy. The energy of retrieving some data from an off-chip memory is very high. You can see that in the table in the bottom right. The capacity 3D stacked memory is like just getting more memory on chip. And we looked at the utility of having those on-chip scratch pads. We know how valuable it is. And 3D gives us another dimension in which we can expand that. And then form factor. It's if we can use some of the memory essentially on chip above the accelerator or below the accelerator, we may not need as many memory packages, and that helps make the form factor considerably more compact. So just comparing, say, the 2.xd solutions, the horizontal solutions versus the 3D, we can get to much higher bandwidths at lower energies. And you can also see that in the graph that's in the upper right-hand corner. So in terms of 3D integration, the current state is it's certainly in production for low power memory stacks because they don't have this kind of thermal concern. For high power memory accelerator stack, that's where we would like to go. But we recognize that there are a lot of thermal challenges. There has been some good headway in this. You can look at the AMD announcements of the 3D SRAM on a CPU. And one way that they skirted a lot of the thermal issues is just by placing the 3D memory directly above the SRAM or the memory portion of the bottom chip, and not really over the higher powered compute cores. Nonetheless, cooling and power delivery are very major challenges for 3D, and there are some innovative things that we've looked at. Dual side cooling is one of them, or taking that even a step further and passing coolants in between the chips is another way of doing that. So let me just switch gears briefly before I conclude, which is to talk a little bit about the IBM chiplet research ecosystem. We are putting a major emphasis on heterogeneous integration and packaging through all of our research sites and integrating with our systems businesses as well. We have an AI hardware center, which has a good number of members, and we are focusing on chiplet technology. We're working on co-packaged optics, something I didn't have a lot of time to talk about here. With a particular partner. And then we have a very collaborative ecosystem which spans the range of equipment, materials, the EDA providers, research, and manufacturing. And in terms of the particular thrusts, these are looking at alternatives to silicon interposers and to 3D. The high density laminate is one of those examples that I mentioned earlier, as is the silicon bridge to connect, say, two accelerators together. And then to continue to grow vertically and look at combinations of accelerators with stacked memory. And we have some nice demonstrations that we've done in this area. Okay, so what is the path forward? I think packaging had always taken a back seat to compute because we were always getting performance much more out of Moore's law and scaling. I think that fundamental paradigm has changed. Packaging has now come to the front seat. It's really a first-class citizen, and that we have to pay more and more attention to, particularly with the driving needs of AI. So that is transitioning us from this regime of classical packaging and, with some heterogeneity to really increasing heterogeneous systems and going to truly heterogeneous compute. So this means creating HI-based accelerator packages in which we could essentially plug and play components and create more and more targeted and domain-specific applications, leveraging the benefits of heterogeneous integration. And this is very, yeah, am I at time?
You are just on time, Arvind. Is this your last slide?
Yeah, I think I have maybe one more, but I can go very fast through this.
Okay.
So as mentioned, there's an astounding range of applications. So chiplets really help us to have Lego building blocks in a way to target specific applications. And I won't, again, go through this table, but you can see that we want to target applications ranging everywhere from the edge on the left to big data centers on the right. And the ultimate vision is that we could create this kind of a chiplet supermarket with a large catalog of components and chiplets that could be bought, and that would greatly lower the barrier to innovation by leveraging these smaller and lower cost dies and the IP reuse. There are a number of obstacles, so this is right now more of a vision than a reality, but there are a lot of organizations that are working very actively towards making this a reality. And let me maybe just summarize here that this is what we think will enable heterogeneous integration. These are the requirements for interfaces between components, and having an open standard which meets these types of efficiency requirements and standards would be a great help in fostering this type of an ecosystem. So let me end there. Thank you.